Okay, so let's continue where we left. We looked at computing the either the strength or the cycles in a fatigue failure. Now we'll get to the endurance limit in detail. So the endurance limit was something we I wrote down as zero point 0.5 SUT or 100 kpsi depending on the ultimate strength. Right now, this is the endurance strength if you look at a specimen in the lab. Now, when you say in the lab, it means it's machined to precision. It is under room temperature and so on. It turns out that those conditions affects the endurance strength, temperature, finish, and so on. And because in the field you don't expect conditions to be ideal, the endurance strength will actually go down. By how much is determined by some of these factors. So if SE prime is the endurance step of a lab specimen, the keyword here is lab, then the endurance strength SE in the field, by field I mean in the operating conditions in your applications, you'll see that SE is less than SE prime due to various factors. Okay, these factors are, there are five factors we'll consider: surface factor, size factor, load factor, temperature factor, and reliability factor. So if you're given the endurance strength in the lab, this is the lab specimen, and this is the field specimen. Then you have these factors Ka, Kb, Kc, Kd, which when multiplied gives you the new endurance factor. All these factors Ks are less than 1. So if they are less than 1, well, or equal to 1, then you can clearly see that Se is actually less than Se prime. Now, the question boils down to how do we find these factors? Again, this is, as I said, the whole course is based on empirical testing, and all these factors come from empirical tech. So, what we'll do is we'll go through each of these factors one by one, and then eventually all will come together in one big problem which we'll solve. And also, we'll solve some small problems which help you to understand how to compute these factors. Okay, so we'll go with all these factors A through E. The first one is known as the surface factor. Okay, so this factor depends on the finish. So you can see that if you have ground finish, machined or cold drawn, hot rolled, or as forged, you will have different values for A and B, and those A and B are to be put in this formula, which involves the ultimate strength or tensile strength, and you get the factor Ka. Okay, so given the surface finish, you can find Ka. That's what it boils down to. Now, for the exam, you do not have to uh, write this down, this particular table in your sheet. I will give it to you. So please don't write it down. It's just going to waste space in your page. Okay. So I'll give this table for you. But in the homework, of course, you have the appendix to refer to. Okay, so let's see how we can use this. The first problem: a steel specimen has a minimum ultimate strength of, the word minimum, don't get confused with it, just the ultimate strength of 520 megapascal. Estimate the factor Ka. So it is Ka with a small k. Okay. Um, so the question is, how do we find the strength? We need to know how it is machined. Say it's machined or it's finished. The finish is machined finish. So we go back to this and see that machined or cold drawn has A given by, well, in this case, we have KPS and MPa, so FPS. So we need to figure out what we have to use. In this case, we're going to use SI because the strength is given MPa. So we can say that we need to use this A, 3.04, and then B is the same irrespective of FPS or SI. Okay, so we have A equal to 3.04, B equals minus 0.2217. To take this, cut, and then paste. Okay, and then the formula is clearly K equals A SUT raised to B. A is 3.04, SUT is 520 megapascals, B is minus 0.217. So Ka, after substituting the values, comes out to be 0.78. So that's the answer. Okay, now if there was everything else was under room conditions, operating or the lab specimen conditions, then if you want to find SE from SE prime, uh, then you'll basically use this. And so you can see that if you put K is 0.78, you'll get SC is less than SC prime because SK is greater than 1. So the effect of machine finish is that the endurance decreases. Okay, that's very important. Okay, next, let's look at the next factor. Okay, the size factor. So the basis of computing these factors in the labs is basically the specimen is rotated. So here you can see that the specimen, let's say it's a round specimen, it's rotated, and then let's say D is the diameter. Then if it's a rotating specimen, like say the shaft of a car is going to, of the wheel of a car is going to be spinning, that is what the that you can imagine when you are computing the size factor here. Okay, so if D is the diameter, then depending on the loading, if you identify the loading to be bending or torsion, so bending would be M. This is, think of M, think of torsion as T. Then you would use these factors. So you'll only use the diameter. Again, this is this is FPS because this is in inches and this is in mm, so it is SI. So depending on the dimensions you have, you could use KB in using FPS or KB in SI. However, if the loading is axial, I'll use P. So axial loading is just stretching or compression, but in the axial direction, then you just use KB equals 1. So what it's saying is that in axial loading, there's no effect of the size factor doesn't really matter. Okay, but if it is bending or torsion, then KB is less than 1, which means bending and torsion, it's going to affect your endurance limit. It's going to decrease the endurance limit. Now, things get tricky when you look at specimens which are non-rotating. Okay, as I said, this is rotating. What happens if it's non-rotating? Now, this is, I just put this for completeness. It's a lot of text here. There is a theory called critical volume theory, which basically, again, it's an empirical theory, which says how do you uh, take a non-rotating specimen and model it as a round rotating specimen. It's basically, the idea here is that you need to take a rotating round specimen, which is shown here, and look at the 0.5% of the area outside the on the rim of the circle. So this is a rotating round specimen. And then if you have any specimen which is non-rotating, then you try to map arcs, or not arcs but sectors in this uh, so-called the non-round specimen, non-rotating round specimen, and then map this area shown in yellow here to the area over there, and then you find an equivalent diameter. So you're trying to sort of, what you're trying to do here is map this area shown over here to the area here. So what is the effective diameter if you map this area to that one? That's basically the critical volume theory. And by mapping that, you can see there's the area computed here, and that's mapped to this area. You can find equivalent diameter. So what it's saying is that if you want to take a non-rotating specimen, you map it to a rotating round specimen and find the effective diameter. Once you find the effective diameter, you just go back and start using these formulas. So the theory is developed for rotating round specimens. If it's non-rotating, you find the equivalent diameter and then use these regular formulas. Now this page gives you how to compute the diameters for non-rotating specimens. So once you get these diameters, here DE for rectangular, DE for circular, DE for I section, we'll not be using these, but these two are the most common ones. So once you get DE, all you have to do is then use it within this framework. Okay, so as I said, size factor depends on rotating ground specimen. That's how we have found these values, and we're just mapping them from. So the question is 0 times. Okay, let me see. 87 d raised to. Let's see. Did I make a mistake in this? Yeah. So this is 0.879 d raised to minus 0.107. So the question is this. Let me rewrite that, and then you can get from context other one. This one is kb equals 0.879 d raised to minus 0.107, and then 0.91 d raised to minus 0.157. So for 0.3 d less than 2 and 2 less than d 10. So yeah, it's 0.879. And similarly, you can see this 1.24, 1.51. This is there's a bit of a problem when trying to write LaTeX related formulas in Word in OneNote. Okay, but that's the formula, and then you'll get other things from context. Okay, so I think the best way to illustrate this is to actually do a problem involving a rotating and non-rotating specimen, and that will make it clear how to use these formulas. So here's a problem for KB. A steel shaft is loaded in bending. Okay, so this is M. It has a 32 mm diameter and a filleted shoulder of 38 mm diameter. Estimate the size factor KB for rotating mode, non-rotating mode. So what's going on here is that there is a specimen which looks like this. And you're given that the diameter here is 38 mm, and then the diameter here is 32 mm. Okay, and we are asked to compute the KB for these two conditions, rotating mode and non-rotating. In one mode, the shaft is rotating, in another mode, it's not rotating. So first, let's do it in the rotating mode. Okay. So KB, okay, the question is we have two diameters here, which one to use? So if you go back here, we'll have to use clearly the one for SI units. So it's one of these two. And clearly this one, because it's bending, right? We are given that it is a bending problem, M bending. So we have to use this formula. And in this formula, we have 32 or 38. Both of these diameters fall in this range. So it has to be KB equals 1.25 d raised to minus 0.107. So let me write down that first. So KB is 1.24 d raised to minus 0.107. So that's clear. Now the problem we face here is that we have two diameters, 32 mm, 38 mm. Which one should you use for this formula? Okay, so here what you want to do is remember what KB is doing. It's basically is a fraction. It's between 0 and 1. The smaller the value of KB, the less is the endurance strength. So if you have two diameters to choose from, 32 and 38, you want to find which diameter will give you a smaller value of KB, because the smaller value of KB means your S endurance is going to be smaller, and so that will make your design conservative. Now, if you want to be more ambitious, then you can choose the larger value, in which case your endurance strength would be it will be less conservative. So I would be on the safer side and use a smaller diameter for D. That way, KB will be less than what you'd get for the other diameter. So use the smaller diameter for this calculation. So you get a conservative value for this. So KB equals 1.24 d raised to 32 minus 0.107. So KB comes out to be 0.855. Okay. Now let's look at non-rotating mode. Okay, so what non-rotating mode means, the specimen is not rotating. If you want to do that, we need to go here. And this is just explaining the theory, but really we are after is this table. This table tells us if the specimen is not rotating, then how do we map the non-rotating specimen to the rotating specimen? So what we need to do is we need to take d equals 0.37d, and that will map it to the non-rotating specimen. So here we'll use this formula. We have an equivalent diameter of 0.37d. So 0.37, in this case, we going with the smaller diameter. So DE comes out to be 11.84. And now we use 11.84 in figuring out KB. So now we have the equivalent diameter. We go back to the rotating ground specimen because we've converted, sort of mapped this to a rotating ground specimen, the non-rotating specimen. So again, we see if it's again in this range between 7.6 to 51, that is 11 is between that. So we use the same formula, 1.4d, where d is the new value we got from the mapping. So KB is 1.24, D is 11.84, and 107. And putting in the value, we get KB is 0.95. Okay, so this is the answer to the second part. Okay, do you always choose the smaller diameter? Yes, because okay, let's do this. Let's use the bigger diameter instead. I'm actually curious. Uh, what will happen if we choose? So let's for A, let's choose D equals 38. So if we use 38, we get KB equals 1.24, 38 times 1.07. Let me just quickly compute this value. 1.24 into 38 times minus 107, 84.84. Okay, so I didn't expect that. I thought it would be larger. Okay, so I get 0.884, 0.84. Let me check 1.24. Huh, interesting. So uh, this value and this value. So in this case, okay, so I should have done this calculation beforehand. I just assumed that the smaller value will give me a smaller KB, but turns out that the larger KB, larger D gives me a smaller KB. So this is going to be more conservative, right? Why it's going to be more conservative is because if you have SE equals KB times SE prime. The smaller the value of KB, the smaller is going to be SE, and smaller KB means conservative. So in this case, it just happens that I chose to be a less conservative value. It's not a big difference, 0.855 versus 0.84. So really, I would say it's a designer's choice. You want to use the one which you think gives you more confidence. So in the field, yes, you want to choose probably what you want. In the exam, which one would you use? I think I would be fine you using either of them. If you use this one, it would be less conservative, 0.855. If you use 38, you get 0.84, which is which is more conservative than this one. So yeah, for it's a designer's choice to answer the question. Okay, an exam, I think I would be fine you using any of the values. Okay, unless I explicitly tell you to be more conservative. So if I tell you to be more conservative, then you want to use this one. This is more conservative. And if I tell you to be less conservative, then use this. So this, by the way, is being less conservative. Why? Because I use a 32 mm diameter to compute this. If you had to use 38, you'd end up with a value which is probably less than 0.95, but it's not a whole lot different. Okay, so that if, hope that answers the question. And Okay, let's move on to the next factor, Kc. Kc is a loading factor. It just depends on the type of load you apply. For bending, it's 1, axial loading is 0.85, and torsion is 0.59. Okay, how did they get this? Well, they did experiments to get this. Um, and that's that. Okay, next, let's move on to the temperature factor. This one is the one which is the most trickiest, and students usually struggle with this one. So let's get this, let's understand this carefully. Okay, so the temperature vector Kd is, you have to know these formulas. St is the ultimate strength at operating temperature T, and SRT is at room temperature. So what it's saying is that normally you will do the test, that is the specimen which was talked right here. This test is done in room temperatures. Room temperature is, you're looking at maybe 70 Fahrenheit. But when you go in the field, if it's a high, if it's a high if the temperature is usually greater, because usually they're either working in extreme temperatures, very hot temperatures, or they're, because things get heated up as you move, or extremely low conditions, which are usually unlikely unless you're operating in the winters. Then you'll have to change the value of endurance based on that. So here, if you are given the temperature in Fahrenheit, you have to use the first formula. If you're given Celsius, use the second formula. Okay. Given that, now let's see how do you actually compute SC prime. Okay, now there are two conditions, two cases. One is you may not be given SC prime. Now, I know I told you a formula to compute SC prime as half of what, SUT, but I could also tell you that that formula is not valid. If that formula is not valid, you assume that SC prime is unknown and you follow this procedure. However, if SC prime is known, it's given to you, specifically it's given to you, then you would use this procedure. Okay, so for first, if SC prime is unknown, you'll estimate the ratio, okay, which is given the previous page. How to get the ratio? You only need to know the operating temperature, maybe 360 Fahrenheit or 200 Celsius. You'll put that, you'll get that ratio. Then you'll estimate the ultimate strength, SUT is ultimate strength, at T, at the operating temperature. This would be at, say, 360 Fahrenheit or 200 Celsius, based on the ratio you computed and SUT at room temperature. So normally, when you're given the ultimate strength, you're given at room temperature. In other words, when they do that stress testing, which we talked about, probably the first class, that's done at room temperature, and that is available to you in any table. This is a way of computing the ultimate strength at a different temperature. Okay. Finally, what you do is uh, you basically find SC prime from this formula. Now, this formula is not new. You have seen this formula before. It's exactly this formula. It's right here, here I think. Yeah, this formula. The difference being that you actually use SUT at the elevated temperature. So this SUT is what you use here. You do not use the room temperature SUT, and this is the point where students get confused. Okay, this is very important that you use the SUT the uh, at the operating temperature, not at room temperature. Okay, and this will become clear when you solve problems. That's the key difference. Now, the other case is where SE prime is known. This is given to you. Then you first estimate the ratio, previous page, estimate KD. KD is simply that ratio. And then estimate SE as KD times SE prime. And then SE prime is given to you, right? It's known. Okay, so I think the best way to illustrate this is to solve a problem. Yeah, we'll solve a problem. Before that, I'll just get into the final fifth factor, and then we can solve a problem. So if you're given the reliability of the specimen, so when we manufacture anything, you say how reliable it is. You say that it will fail, it will work 99% of the time and fail 1% of the time. So then that would be the reliability. And depending on the reliability, you can compute a factor KE. This is what you need, KE. So either you compute KE from here, just a table, or if you're given just ZA, some transformation variable, then you can put it in this formula and get it. This just makes your life just an extra step. But normally I will just give you this. Okay, I'll just give you that and you can just read off the KE. So KE is very easy. KC is very easy. The one which is more involved is, I would say, the temperature one, because you have these two cases. And another place which is kind of involved is these rotating or non-rotating one. Okay, so what we'll do is we'll solve two problems now, which will illustrate um, these things very well. So first we'll do a problem only on temperature effect, and then we'll solve a real is it here? Yeah, we'll solve another problem where you have all the factors coming in. So here is a problem on just temperature effect. Say 1035 steel has a tensile strength of 80 kpsi. So SUT, and I will be very specific here. This is at room temperature, 80 kpsi, and to be used for a part that operates at temperature 750 Fahrenheit. So SUT, well, you're given SUTT is not known, but T is 750 Fahrenheit. Estimate the endurance limit at the operating temperature. Okay, so we want to compute, this is, I don't need this, but T is given to us. And then you also told that room temperature is 70 Fahrenheit. That is, in this equation, when you found endurance ultimate strength, it was at 70 Fahrenheit. That's room conditions, room temperature. Okay, estimate the, now we asked to compute the endurance limit. What is the endurance limit is SE, and SE without the prime, because SE normally at room temperature is known, and you want to know SE at a temperature of, in this case, 750 Fahrenheit. Only the tensile strength at room temperature is known, and at the room temperature of 70 Fahrenheit, the endurance limit for the material is found to be SE prime 39 kpsi. This is basically these two cases. In one case, you're given SE, that's case B. In case A, you're not given SE prime. So let's clearly identify that. So the first part of the problem, A, is SE prime is unknown. Okay. So we just follow this recipe. We estimate this ratio, we estimate SUT at T, and then we use this formula. So 1, 2, 3. Let's do 1, 2, and 3. So number 1, we estimate ST divided by SRT, and that is the formula over here. Okay, I'm going to write the one for Fahrenheit because it is in Fahrenheit. So it is 0.98 plus 3.5 10 raised to 4 TF minus 6.3 10 raised to negative 7 TF square. I write it properly. Liquid meter. SRT equals 0.98 plus 3.5 TF minus 6.3. Okay, so we put TF as 750 and then solve for ST divided by SRT. It comes out to be 0.7, sorry, 0.89. Okay, that's step one. Step two is we need to compute SUT at operating temperature. That is simply ST divided by SRT times SUT at room temperature. Okay, ST divided by SRT is 0.89. SUT, this thing is given here. It's 80 kpsi. So SUT at at operating temperature comes out to be 71.2 kpsi. So that's step two. Okay, and then the final step, which I can show you here, is we got just going to use these formulas. So we know that first of all we are using FPS units, so it's one of these two. Since SUT is less than 200, it is 71.2 kpsi. Its SE prime is simply 0.5 SUT. So third step, SE prime is 0.5 SUT, but now you will have to use the operating temperature value, 0.5 times 71.2. So SE prime is 35.6 kpsi. Okay, so that's the answer. Now we can move to the next part. This is SE prime. Sorry, my bad. This should be SE, right? Uh, we just be careful about this. So what did I say here? Let's say SE is SE prime is SE, whatever is here. So just to be complete, let me just write it the way it is in the formula. So this is SE prime, but SE is SE prime is 35.6. So now we are correct based on what I wrote down in the notes. Okay, the second part, B, SE prime is unknown. Sorry, is known, right? SE prime is known. In fact, we're given the value of SE prime as 39 kpsi. At the room temperature of 70, the induced limit for the mirror is found to be 39 kpsi. So SE prime is 39 kpsi. Okay, so let's go ahead and use that that recipe for computing when SE prime is known. First, you estimate this ratio. We know it's 0.89. Then KD is just ST divided by SRT. We know KD because we know the first part. And then third one, we just use this formula. So we have part one, ST divided by SRT equals 0.89. Okay, we have done this in the previous part, so CA. Second part is KD equals ST divided by SRT, so it is 0.89. And the third part is SE is KD SE prime, so it's 0.89 times SE prime given to us 39. So SE comes out to be 35 kpsi. Okay, and they're not too off. If you see this value and this value, they're very close. They're very close to each other. Okay, so this is how you have to use the formulas to compute the temperature factor. If S is known, S is unknown. Okay, so now we'll get to the part which will get all the five factors together. Last problem. So a 1080 hot rolled steel bar has been machined to a diameter of 1 inch. It is to be placed in reverse axial loading for 70,000 cycles to failure in an operating environment of 650 Fahrenheit. Estimate the endurance limit and fatigue strength at 70,000 cycles. Assume reliability for the endurance limit estimate to be 99% and ultimate strength SUT at 70F to be 112 kpsi. Okay, so the question is what is asked here? So we need to estimate the endurance limit and fatigue strength at 70,000 cycles. So first thing is endurance limit. That is the first part. And the second part, we need to find fatigue strength, that is SF, at n equals 70,000 cycles. Okay, now this is between what, 1,000 and a million cycles. So probably we can use this formula, right? Where n is given to us, a and b can be found if we know. So we know that a and b is a function of f, se, and sut, right? So if we go back to the previous section, we saw this formula. It was right. Uh, yeah, here. So a, b depend on sut, se, and f. So going back, A, B can be found if you know F, SC, SUT. F, we know there's a formula which is based on that curve, but F depends on SUT. So once you know SUT, you can find F, and SE has to be come from the first part. So really, it's clearly a demarcated problem where you need to solve for A first before you can attempt B, because part B depends on A. This is actually a poor choice. I just realized there's A and B, and I put A and B. Let's just call this something else. Let's call this uh, maybe 1 and 2. Okay, so it's not confused with this A and B. Okay, so let's solve part A first. For part A, it is Ka, Kb, Kc, Kd, Ke, Se prime, right? Se prime, I think, is not given to us. Okay, so we are not given Se prime, but we can use the fact that if Se prime is not given, how do we compute Se? Is something which you have talked about in the temperature effect. So we can, I think we can solve this. Okay, so let's get started and solve this one step at a time. Let's do Se first. Compute Se. Okay, so we just get into the various factors. Now, here's an important thing. Uh, we could start with factor A, the size factor, but the problem is that we do not know Se, and that is something which is of concern. So you want to first start with the temperature factor because that will give us Se, and then we can figure out the other things. So in any problem where you're not given Se prime, but you're given a temperature effect, you want to first start with Se prime and then move on to other things. So let's start with the temperature factor. So start with temperature factor as Se prime is unknown. Okay, this problem is a problem in FPS units, so we have to use uh, the first formula for uh, the ratio. So let's do that. So SC prime is unknown. So the first step is ST divided by SRT is 0.98 plus 3.5 10 raised to negative 4 TF minus 6.3 10 raised to negative 7 TF square. TF is the temperature at the operating conditions. It is given as 650 Fahrenheit. Okay, so if you substitute this, you can solve for the ratio. It comes out to be 0.94. Okay, that's the first step in this three-step algorithm involving computing the SE prime. The second step is we compute SUT at operating temperature is ST divided by SRT times SUT at room temperature. So SUT at operating temperature of 650 Fahrenheit is 0.94 already computed, and SUT is given as it's given as at 70F is 112 kpsi. Okay, so this comes out to be what is the exponent on the second 10 in equation? Oh, it's minus 7. Hope that was what was asked. Yeah, I think that's the one. So 0.94 times 112 is 105 kpsi. Okay, so that's the step 2. Step 3 is we need to compute what SC uh, prime is. SC prime, you have to go back to, let's just show it to you. We are in this particular algorithm. We have to find it based on SUT value. The SUT was 105 kpsi, which is less than 200. So we have to use 0.5 SUT. So it's 0.5 SUT, and this should always be at operating temperature. So 0.5 times 105. So SE prime is 52.5 kpsi. Okay, so we've got SE prime, which means we can now turn ourselves towards the other things, which are the other factors. We'll get, and of course, I forgot to say this. This means KD is 1, right? So if you go back here, you just KD is just 1. So KD is 1. So we've got one factor, and we've got SC prime. Let's compute factors A, B, C, D. Well, D is done. So A, B, C, and E. So to get factor uh, A, we need to figure out what is the machining. Machine to a diameter of 1 inch. So if it's machined, so we have to use machined. We have to use, since it's kpsi, we'll use a factor of 2. Is it machined? Let me just check. Something else in my rule. Oh, sorry. It's hot rolled. Hot rolled steel bar has been machined to. So what's the difference? Cold drawn, hot rolled. I guess you go with the. It's hot rolled and then machined. Uh, there's some ambiguity of which one to use. So I'll go with the hot rolled. Um, Yeah, let me just go with the hot roll here. Uh, I should be more clear, explicit about what factor to use. So hot rolled is what we'll go with. I'll be very careful about what I give in the exam, but let's go with hot rolled. For hot rolled, we have A equals 11, B equals uh, minus 0.65. Got hot rolled. So Ka is A times SUT raised to P, but there's a catch here. You need to use um, what do we have? So this SUT now has to be at the operating temperature. That's the key. So what we had computed for SUT is 105 kpsi. So note this is the one. Don't use the room temperature one. That's why we actually computed the factor KD before we computed other factors. So 11 times 105 raised to minus 0.65. Just highlight this. So from this we get Ka equals 0.534. Okay. Next, KB. Okay, read the question. Machine to. Okay, so keyword here is actually loaded, actual loading, because factor um, KB, if you see KB, we need to know the act loading. So actual loading, so KB is 1, so it makes our life easy. So KB is 1. Okay, so KC is the loading factor. So actual is 0.85. Actual 0.85. This is also for actual. Then KD, we already computed, we don't need KD. This is previous page. And then KE, this is the reliability. We are actually told it is 99% reliable. So if we go to reliability factor for 99, we have 0.814. Okay, with that we are all set to compute SE. SE is KA, KB, KC, KD, KE, SE prime. So Ka is 0.534, Kb is 1, Kc is 0.85, Kd is 1, Ke is 0.814, Se prime from the previous page is 52.5, and so Se comes out to be 19.39 kpsi. Okay, so what you notice here is that even though Se prime is 52.5, the effect of these factors got the Se prime to 19.39. So the specimen, which is actually pretty strong in the room conditions in lab specimen, is becomes kind of weak when you take it to the field, right? This is what it brings. It drops it by a factor of almost what? 2.5. Okay, so with that, let's get to the next part. We have to compute for second part. We need to compute SF when n is, I think, 70,000. Okay, so for this, we need A. A is F times SUT square divided by SE, and B is 1/3 log to the base 10 SE divided by FSUT. Okay, so now we have to find SUT. Now, always when you know the SUT at operating conditions, you want to use SUT at operating conditions. That would be 105 kpsi. This is very important. Do not use the value at room temperature. Next is F. Okay, now how do we get F? Well, if you look at the problem, we need F is a function of SUT. So SUT is 105. So we go here and 105. Okay, it's something above 0.83 but less than 84. I would just put it between, how about just using 0.835? 0.835, because this is 0.83 and that's 84, so 835. You could also use this formula where you put SUT equals 105 and get the value. So let's just use 835. 0.835, so 835. I'll say CFSUT in, that would be lecture 15. Okay, so F is known. SE, we know it is 19.39. That is a calculation we just did. So we can now compute A. Putting all this inside that equation, we get 401.2, and that is kpsi. And B is unitless. B is minus 0.22. Okay, so finally SF equals A times n raised to B. A is 401.2, n is 70,000, B is minus 0.22. SF comes out to be 34.47 APSI.